Very good. Okay. Good morning, ladies and gentlemen. So welcome to this session. I'm very glad to be here with you today and very delighted actually to share with you our experience. And I'd like to start by thanking the organizing committee for giving me the opportunity to talk to you today. So the title of my talk is The Promise for Deep Learning in Multimodality Medical Image Analysis. And I think you agree that this is a sufficiently broad topic. I can probably talk about this the whole day. So this is going to be one of these talks where we sort of have sections, we go a little into detail in other sections, we sort of skip over, and hope to have some time for questions if anything is missing from anybody's expectations. All right, so let's get started here. So given the virtual nature of this meeting, so this is our website, by the way, so where you have access to our research projects and obviously can consult also our research publications. So just give you an insight of basically the material that I'm going to use in this presentation. This is not really an outline of this talk, this kind of list of topics I'm going to go through. So I'll start very quickly about going through the advances in multimodality and molecular imaging. And then so go a little bit through the history of artificial intelligence and what is the motivation behind its use in multimodality medical image analysis. So I'm going to focus on the topics that you see here. So basically denoising of low dose CT, PET, SPECT imaging. I'm going to introduce those imaging modalities later on, and then the applications obviously multiple, so again from chest in X-ray CT imaging, brain in PET imaging, cardiac imaging in SPECT, and then I'll go through the medical image segmentation, both in CT and taking as an example, say COVID-19, which is obviously a timely topic, and then I'll share you our experience in the area of medical image segmentation in positional emission tomography. Cross-modality image conversion is a very hot topic as well, and then I'll show you some examples here. Quantification, so is one of our research topics, very active research topics, and I'm going to show you some examples as well. And I think I won't have the time actually to talk about the last topic here, and then I'll summarize this talk and give you also my thoughts about possible scenarios for future perspectives. So I think personalized medicine has where each person's or patient's unique genetic profiles is using the detection, treatment, or prevention of disease is a very timely topic as well. So personalized medicine is possible because new powerful technologies can be used for this purpose. And I guess you can see here, so the basically the move from two-dimensional projection imaging to three-dimensional imaging and the introduction of 4D imaging, where basically so combine the 3D information that we gather from either X-ray CT or positional emission tomography and combine this with the time information, which is the fourth dimension, to gather the information about the moving targets such as the heart, or we can also gather information about the kinetic processes taking place in vivo, and through the use of hybrid imaging modalities, we can also get the information about the fifth dimension. So this is very important actually for a number of research applications that I'm going to talk about later on. So just to go through the imaging modalities that I'm going to talk about today. So this is the principle of X-ray compute tomography. So we've got an X-ray tube, so rotating about the patient, and then you get a bunch of X-ray detectors on the opposite side, so basically behind the patients, and then we collect data by rotating the X-ray tube and the X-ray detectors around the patient. So we collect a number of projections throughout all the views that we store in the format of a sinogram. So basically each point in each in this matrix here reflects a line of response, and in the x-axis, so we obviously have the bin or the distance from the center of rotation to each line of response here, and in the y-axis, so we have the views or the angles actually reflecting the angle between each line of response in yellow and the y-axis, which is basically vertical in this case. And the aim of image reconstruction from a projection is basically to invert the procedure, or basically recover or reconstruct the images from the measured projections. So the most widely used techniques until very recently was the filtered back projection algorithm, where we basically filter the projections in Fourier space and the back project them a line of response by line of response to get the reconstructed images from the measured projections. And more recently, iterative reconstruction techniques or statistical reconstruction techniques were introduced in the clinic, and obviously improving substantially the image quality and the quantitative accuracy as well. So on the molecular imaging side, this is kind of timeline for the development of this imaging modalities, starting from the discovery of radioactivity by Pierre, Marie Curie, and Becker. So they shared the Nobel laureate in physics in the beginning of the 20th century. And then you see also a number of pioneers actually who developed tools or techniques or apparatus that has been instrumental in the development of these imaging modalities. So for instance, we can cite Lawrence, who developed the cyclotron that can be used actually to produce radioactive material that can be used actually to produce radio tracers. George de Hevesy is a Hungarian biochemist who's known to be the father of nuclear medicine, who introduced the tracer principle, and he's again a Nobel laureate, 1935. Anderson, who discovered the positron. Without a positron, there would be no positron emission tomography. And you see also Engel, actually, who developed the Engel camera in the 50s. Cherpugosian, Hoffman, who developed the positron emission tomography. Bruce Hasegawa, who introduced hybrid imaging in the form of SPECT-CT. And as I mentioned, it's a number of other pioneers actually who contributed to the history of molecular imaging during the last 2 centuries. So starting from the basics here, so basically we are imaging positrons for getting positron decay, and that means the proton becomes a neutron, so slowing down till it's slow enough, hangs around electron long enough till we get annihilation, and the projection of 511 keV annihilation photons, which are more or less 180 degrees apart. And so the measurements of tissue concentration of positron emitting radionuclide is based on coincidence detection of the 2 annihilation photons. And obviously, so the positron range depends on the energy of the positrons, and it's quite variable. So going from the less than a millimeter for F18 to more than 1 millimeter for barium-82, which is used for cardiovascular imaging. So as I mentioned, so the detector area actually basically surrounds the patient, detects the emerging annihilation photons, and then the coincidences are collected for each line of response and stored in a 2-dimensional array, or what we call a sinogram. So these are typical images that can be gathered with such a device, and I think you can guess that this is an image of myocardial perfusion. So basically, so the same technique as I mentioned before, so reconstructing the images from the measured projections, and this basically reflects the perfusion in the myocardium. So the first integrated systems combining positron emission tomography and X-ray scanner was developed by a physicist called Townsend and his colleagues at the University of Pittsburgh in the US in 1998. And the idea basically is to combine the imaging chains of Siemens Somatron series scanner with the NICAT rotation PET scanner. So both the CD components and the PET detectors basically so cover more or less so a partial axial field of view of the body, and then the 2 systems share basically a common bed that can be translated between the centers of the 2 PETs of the 2 scanners, which are actually offset by 60 or 80 centimeters, so depending on the scanner manufacturer. So the first PET-CT prototype was operational at the University of Pittsburgh in 1988, 2008 till August 2001, and around 300 cancer patients were scanned on this device, and the success of these initial studies prompted significant interest into by the major medical imaging companies and who commercialized such devices in the future. And just you can see here, so the scout scan, the spiral CT, the PET image, and then the combination of the two and fusion, which can be presented basically to a medical doctor for clinical diagnosis and interpretation. So magnetic resonance methods are non-invasive imaging techniques that provide tailored multi-parametric information on the human anatomy, function, and metabolism, and the sensitivity, specificity, spatial, and temporal resolution may, however, vary depending on the hardware, for instance, field strength, gradient strength, and speed, and the software usage, which can be also optimized for different protocols and for various techniques. So MRI is basically multi-parametric imaging modality by nature, owing to the large number of sequences and contrasts that can be generated. And obviously combining this imaging modality with the specificity of multi-tracer PET imaging enhances the specificity for better characterization of complex disease processes. And these are basically some of the systems that have been commercialized so far. So we see here on the left side the Ingenuity time-of-flight PET MRI system commercialized by Philips and installed in our facility in 2010, so more than 10 years ago. So this is one of an example allowing sequential acquisition of aligned PET and MR images, and a number of such systems were deployed worldwide, and the PET system was actually fully characterized and demonstrating that the performance is not compromised by the presence of strong MR magnets. So the design concept of concurrent brain PET scanner was further exploited to build the Siemens Healthcare Biograph MMR whole body PET MRI system, which was also installed in a relatively large number of institutions, and more recently, so simultaneous PET MRI system commercialized by General Electric called the Signa, based basically on MR compatible silicon photomultipliers that enable the implementation of time-of-flight capability, was also introduced in the market by this company, and similar technologies were also introduced by United Imaging more recently, and I think they got the FDA approval last year, and the system is also commercially used in a number of institutions. So these are just representative images generated by a hybrid PET MRI scanner showing typical image quality, and obviously the high soft tissue contrast on MR images, and also the high definition of the myocardium on gated PET MRI images as well. So in the number of applications are being actually investigated, and I think this is still a hot topic that is being actually looked at by a number of clinical facilities equipped with such systems. So more recently, so there's a consortium called the Explorer Consortium, built the world's first total body PET CT scanner. So this is a kind of 194 centimeter axial field of view scanner, sufficient to cover for the first time the entire human total body in a single acquisition, so in more than 99% of the population, and alone total body pharmacokinetic studies with firm durations as short as 1 second. So this is not a new concept per se, because I mean the idea has been already mentioned and reported by a number of investigators, but this group was basically the first one who managed to get a large funding from the NIH in the United States, so more than $15 million, and then managed to build in collaboration with United Imaging, so the company that I mentioned before. And these are basically the PIs of this consortium, so Simon Sherry, Ramsey Bedoui, and Terry Jones, very proud of the system. Actually, they have designed it, and they published recently a number of research articles reporting on the performance assessment of such a system and the clinical assessment also. These are some of the images they published in their GNM paper 2019, where you can see that basically you can decrease the acquisition time to a few seconds and get diagnostic quality images. And here on the right side, so obviously you can see that we can gather sufficient kinetic data with sufficient sampling to extract kinetic parameters, and this is also has some clinical relevance and very important actually for research applications of device as well. So getting back to the topic of today, I'm not going to go through the whole history of artificial intelligence, but basically we know that AI started in the 40s and different algorithms were developed during the last few decades. So after passing from dark ages, thanks to the data availability and GPU computation 2020, so it's rising again through the development of convolutional neural networks. There were actually, I think, in the history of AI, two major winners. So in 7480 and 8793, and several smaller episodes also, including the failure of machine translation, the abundance of connectionism, and a number of other historical issues that impacted actually this technology, and the fact that the governments, the UK and the US also stopped funding these AI projects in the 80s and in the 90s, and giving basically the option to other more important research to be funded. So, and then starting from 2010 specifically, so there has been renewed interest into these technologies, and I think we now AI entered its a golden age. So basically, so since the watershed moment of 2012 and the subsequent success of deep learning algorithms outperforming other competing classification algorithms, so we can see that there is a kind of large class called artificial intelligence, and within this a large class of AI. So we have a smaller class called machine learning that basically consists of computer algorithms that can learn from inputs to produce the desired outputs. And within this large class of machine learning, we have a smaller class called deep learning. Actually, these are algorithms with hidden layers, which are modeled after biologic interneurons that take in a set of inputs and produce basically the desired outputs. So I've taken this nice illustration actually from a very nice paper published by Hosni and colleagues in Nature Reviews and Cancer. And this plot basically outlines the performance levels of AI and human intelligence, so starting from the early computer age and extrapolating into the future. So early AI came with the subhuman performance and varying degrees of success. So currently we are witnessing now task-specific AI applications that are able to match and occasionally surpass human intelligence. And it's expected that general AI will surpass human performance in specific applications within the coming years. So humans will potentially benefit from the human AI interaction and bringing them in to higher levels of intelligence. So another illustration from the same paper. So we've got kind of schematic outlines of the various tasks within radiology where AI implementation is likely to have a large impact. So the workflow comprises the following steps. So starting with the pre-processing of images after acquisition, image-based clinical tasks, which usually involve the quantification of features. So we're either using engineered features with traditional machine learning or deep learning, and reporting results to the generation of textual radiology reports, and finally their integration with patient information and multiple data sources. So AI is basically expected to impact image-based clinical tasks, including the detection of abnormalities, characterization of objects and images using medical image segmentation, diagnosis and staging, and the monitoring of objects for diagnosis and measurements of treatment response. Just actually to show you the interest in this in AI by commercial companies. So due to unprecedented success in tasks such as image classification, so AI emerged as a new tool in image reconstruction with the potential change paradigm in the field. So a couple of scanner manufacturers actually published white papers basically reporting on the implementation of AI algorithms in their clinical environments. And basically, so we've got two phases during the clinical implementation of this technique. So the first phase is the training, where we basically have a bunch of low quality images and the high quality images of the same subjects. These are used for the training, and then the operational phase in the clinic, where we basically acquire only the low dose images and generate high quality images from those low dose images using the developed AI algorithms. So these two companies are, I think it's not a surprise, Canon and General Electric, and the two of them published white papers actually describing those algorithms. Not going to claim too much, so this is just an illustration of the algorithm, some images published by those companies. So this is a data set of the same patients reconstructed with the conventional filtered back projection, 2 millimeters slice thickness, and this is the reconstruction with the deep learning based strategy. They call this ACE, and I think you agree that the image quality is much improved with the deep learning based strategy, and the noise actually that you see here in the liver is significantly reduced by the AI based algorithm. And this is also the true fidelity algorithm by General Electric, where you see also the comparison between conventional filtered back projection, statistical iterative reconstruction technique called IEEE. And obviously many radiologists complain actually about the plastic nature of iterative reconstructions for X-ray CT, and much improved image quality that can be achieved with deep learning reconstruction, as you can see here. Right. So one of the issues actually that has been reported recently in this PNAS paper by scientists from Cambridge in collaboration with other institutions is that there are some instabilities actually in the implementation of deep learning strategies for image reconstruction, and they nicely actually did a very good simulation study in elegantly showing the limitations of AI-based algorithms for image reconstruction, and they nicely illustrated this with some examples from magnetic resonance imaging. And you see here, so when they kind of introduced some instability artificially into the images and demonstrated that the AI-based solutions fail actually to recover the grounded truth of the reference images, and you see some artifacts in this area. So I think we have not reached yet the maturity that enables the implementation of those techniques in the clinic. So still a long way from their clinical adoption. So another very nice paper published in Nature Biomedical Engineering from people from the group of Leipzig from Stanford. They reported on a really impressive technique that enables to reconstruct three-dimensional tomographic images from planar X-ray radiographs. And this is basically the principle of the technique. And we obviously know that we need a pretty large number of projections if we are going to reconstruct the images using classical analytic reconstruction techniques, and probably less number of views are needed when we use regularized iterative reconstructions. And the idea actually is to reduce the number of projections, taking into account the sparsity of the data acquisition process, and to reduce the number of required projections to really minimum. And this is what they did in this nice work here, without going through the details and the architecture of the networks they use it. So basically the training set included planar two-dimensional projections and three-dimensional volumetric X-ray CT images of the same patients that were used actually for the training. And then they apply the same methodology, actually trying to predict three-dimensional images from the two-dimensional planar radiographs of some subjects. And they nicely reported so excellent image quality and very good performance. You basically see here the testing samples and the predicted images, so very good agreements between the predictions and the images actually that were used as inputs. So starting from our experience in the field here, I'm going to share you our experience in this area during the next 30 minutes or so. So try to make this talk in less than 15 minutes, so just to allow time for questions. So we start actually with the presentation of technique that we developed actually to reduce the acquisition, to reduce the radiation dose delivered to COVID-19 patients using deep residual neural network. So what we did is that we took a pretty large number of clinical studies acquired actually with the full dose CT protocol, and then we used this data to simulate low dose CT images. So basically by playing with the parameters, so reducing the radiation dose delivered to the patient, so the CTDI, the tube current, the pitch factor, and the voltage, and so on. So a validated simulation technique was used, and this basically shows you, so without going through the details again of the architecture that we have used it. So these are the full dose images of a single subject, one of the patients. These are the low dose images actually simulated from the high dose or the full dose images. And these are the predicted full dose images using the artificial neural network. So the technique actually performed very well on a pretty large number of patients, almost 99, but we got a few outliers. So we know that AI is basically black box implementation of complex algorithms, and that might fail in some cases. And this is one of the examples. You see the full dose, low dose, and the predicted images. So basically enhance the image quality. So there's less noise, but the issue is that in this outlier, so the deep learning algorithm improved the quality, as I mentioned, but changed the patchy lesions to consolidation in the predicted images. So basically changing the interpretation of the COVID-19 images. And these are some of the quantitative measures. So we asked a number of radiologists actually to assess image quality. So giving and assigning scores going from 1 for uninterpretable to 5 reflecting excellent image quality. And you see that the full dose so achieved 4.72 as a score, which is very good. And then our predicted full dose images achieved 4.42, not far from the full dose images, and obviously, so we save radiation dose to the patient substantially. And the low dose images so achieved 2.78. So the images were kind of between poor and adequate image quality. And what was more important actually was the characterization of the COVID-19 lesions. So the overall results associated with the assessments of image quality, as I mentioned, were good. And the frequency of occurrence of each lesion type and the different series of images is shown in these plots. And as can be seen, so what we call the GGO, so has the highest occurrence in all images, and was mixed, all had the same occurrence for all images. And then there was also a small variable, a small difference between the full dose and the predicted images. And obviously the low dose images so were less performing in this respect. So the second application here is basically the segmentation of COVID-19 lesions, which can be also performed manually by radiologists. But I mean, if you talk about some countries like Iran, where they have pretty large number of cases, and then it takes ages actually for the radiologist to delineate the lungs and the malignant lesions manually. So the aim actually here is to implement a deep learning algorithm to reduce the variability of complex manifestations. And so this work was presented actually by one of my PhD students, so Isaac, and he won the best research presentation abstract at the European Congress of Radiology in Vienna recently. So basically, so the AI-based solution consists of a training phase, as I mentioned, and the idea is to segment the lungs and the COVID-19 lesions. So we use it actually heterogeneous sets of patients, going from mild to moderate or severe lesions, and then we use the multicentric data sets with data acquired in the United States, in China, Russia, Italy, and in Iran. So obviously the idea is to give as an input so the CT image, chest CT image of patients that goes through convolutional neural network, and then at the output, so we get the lungs and the COVID-19 lesions, which is very helpful actually for the radiologists to draw their reports. So these are some of the images from the different centers. So comparing manual segmentation with the predictions, so in green and blue here for the lungs, and then in red and blue for the COVID lesions. Maybe you don't see them very well, even if I zoom here. So let me just show you the animations here. So this is radiologist segmentation, the manual segmentation of the lungs and the lesions. And this is the AI algorithm. So the deep learning network with the segmentation of the lungs and the COVID-19 lesions. So again, very good agreement between the manual delineation by the radiologists and the one by the deep learning network. And these are basically 3D contours from 3D representative clinical studies. So the first one with mild pathogens, so small lesions here, moderate and severe pathogens in the last case here. So probably you see it better here in the 3D illustration. So again, comparison between the manual delineation of the lungs and the COVID-19 lesions by the radiologists, and the one achieved by the deep learning algorithm. And again, you see, I think, very nice agreement between the two. Very good. So on the quantitative image interpretation side, so what you see here is basically the plots actually reflecting the image segmentation metrics, again, from the DICE coefficient to Jacquard index. So people active in image segmentation, I think they're very familiar with those quantitative metrics. So we expect actually, so in the ideal case, DICE coefficients close to 1. And I think the performance was quite similar. Probably the standard deviations was higher in some cases compared to others, but overall, so I think we achieved a very good performance for the clinical studies gathered from the different centers. So another application actually very relevant to radiology is what we call the computation models that can be used actually for the assessment of radiation dose to the patients, and especially for pregnant patients that need an X-ray, an abdominal X-ray CT scan, and they're very anxious to know about the radiation dose delivered to the fetus and what are the consequences. So basically, so through the history, so we know that the computation modeling started from the very basic modeling of the human body with the sphere that was in the 60s, and then use of mathematical phantoms, using basically equations to model different organs and the outline of the body, and then through the introduction of anatomical imaging modalities, 90s and the 2000s. So the complex models were developed to which, so basically people added the capability to use mesh models or nervous models actually to simulate or to emulate the respiratory motion and cardiac motion, and also to model patients in different postures. And we expect that in the near future, so hopefully each patient coming for diagnostic imaging exam, so will have his own computation model that can be used for radiation dosimetry calculation. So those models are extremely realistic. So you see actually the different organs here, and the idea is that so we had some experience actually in development of very complex computation models for pregnant patients at different gestation periods, and the segmentation also of thoracoabdominal data sets actually to excite the different organs for patient-specific or personalized dosimetry calculations. And we developed also a series of non-human primates models that can be used also for radiation research. And this obviously takes weeks or ages to segment manually to delineate the different organs and so on. So the idea here is to come up with a deep convolutional neural network that can be used with confidence actually for constructing convolutional models and then for radiation dosimetry calculation. This is what we did actually for the pregnant patients study. And again, without going through the details of the computational model that was used, these are the results pictorially reflecting the original city images, the manual segmentation of those images by qualified radiologists, and this is the output of the automated segmentation, so performed by the deep neural network. So very good agreement, as you can see from these two cases here, so showing the three-dimensional views of three-dimensional display, and I think the agreement is highly appreciated here. So for the left or for the right case, so very good performance, and I think we can rely on those models actually for radiation dosimetry calculations, which is basically the targeted objective. And what we did here is that we look into the radiation dose delivered to different organs of pregnant patients, including the uterus that was confounded basically with the fetus, and we see only very small actually difference between the radiation dose calculated when using the computational model segmented manually by the radiologist versus the deep neural network. And so apart from the lung, where we have also large standard deviation here, I think the performance was quite acceptable for other organs. Another application, as I mentioned, is the segmentation of position emission tomography images, and then we'll focus it here on head and neck images. So this work is was recently submitted for publication, so it's not published yet. And the idea here is to compare three state-of-the-art deep learning algorithms, so residual network, NN units, and the dense VNets with 8 different loss functions that are basically summarized here. So ended up with the 24 deep learning based segmentation techniques that were compared, and with the pretty large actually database in this case that was split between training, validation, and testing. And these are the data from our institution, so HUG for Hôpital Universitaire de Genève. We'll basically compare against the manual delineation of the lesions by the radiologists versus what was basically achieved by the 3 different neural networks. Just to show you the examples here, these are data from the TCIA, so published by the NIH in the United States. These are publicly available data sets that can be used actually for the implementation, the assessment of novel techniques. And I think if you look to the 3D displays here, so the dense VNets, the residual network, and the NN units, so the manual segmentation, when compared to the different neural networks, there are some differences, and obviously the overall performance is acceptable. And if you look to the detail, so this is a busy slide here showing the quantitative performance of those of those algorithms, I think we achieved the highest dice coefficient compared to what was reported in the literature. So between 84 and 86%, which is actually quite high, and I think it outperforms most of the techniques actually reported in the scientific literature. Another application is the denoising of positron emission tomography data, with the deep learning guided low-dose imaging technique for brain patch imaging. And basically the idea here is to implement the deep neural network actually in both image space and in sinogram space. So the concept actually is that we use about 100 clinical studies where we use the small data actually to reconstruct the full dose images, so corresponding to 20 minutes acquisition time with the injection of about 220 megabecquerel. And then we use the list mode data actually to decimate low dose scans corresponding to 5% of the total acquisition time or of the injected activity. And we did the training of the data sets both in the image space and in the sinogram space, and we compare the two techniques. So we use a conventional unit here, and this is basically the output. So comparing the full dose images, as I mentioned, corresponding for this particles study, so to injection of 200 megabecquerel or 20 minutes acquisition time. This is the low dose image corresponding to 5% only for the total acquisition time or of the injected activity. So we divide those by factor of 20. And this is the prediction in the image space versus the prediction in the sinogram or in the projection space. So the assessment actually enabled to conclude that the implementation of the projection space improved the image quality and enabled to get rid of some of the artifacts that we see here. So we see major differences actually in those areas depicted by the arrows. And if you look to the bias maps, so basically comparing the images with respect to the reference of the gold standard full dose image, so you see that the low dose image does a good job actually in terms of bias, but the image quality was significantly deteriorated. And for the deep learning network, so the performance of the implementation projection space outperformed the implementation in the image space, as reflected also by the scores actually assigned by the radiologists, so nuclear medicine physicians, again, assigned scores given between 1 to 5, and you see that full dose images achieved a score of 4.47 compared to 4.1, which is actually very good for the deep learning network implemented in sinogram space. And then we performed a region-based analysis or ROI-based analysis of the whole brain data sets. So we used actually an atlas called the Hammersmith Atlas, where we basically split the images into 83 brain images, and then we do the comparison region-wise. And we noticed that the bias was significantly reduced by the deep learning network implemented in the sinogram space, as you can see from these plots here. So we happy with the conclusions achieved actually with for brain imaging. So we implemented similar techniques using two different neural networks for clinical oncology scans, so what we call basically whole body scans. So again, basically from the thigh to the skull here. And we used actually two different neural networks for this application. So the ResNet, or the residual network, they sort of cycled again. This is an X-ray CT image of one representative clinical study. The full dose patch image corresponding to 3 minutes acquisition time per bed position. So each bed position covers basically so close to 21 centimeters. This is the axial field of view of the PET scanner used to acquire those data sets. And this is the low dose scan, so a sequential scan that was acquired after the full dose scan, where you see that the image quality was significantly deteriorated. The images were extremely noisy. And these are the predictions using the residual network and the cycle gain. And again, so we asked our nuclear medicine physicians to interpret those scans, and we split actually the whole body scan into a brain area and a thoraco-abdominal zone, which is the one that is depicted here in yellow. And if you compare the two, so you basically can appreciate that the scores actually assigned by the MDs was quite high for the full dose images, which was expected anyway. But the performance of the cyclid GANs was terribly good for the brain, and quite reasonable and acceptable actually for the neck plus trunk region. So more important actually, so what was important in this study, so compared to other studies reported in literature, is that we performed a full clinical assessment, not only looking to the image quality, but also to lesion detectability issue. So from the 20 clinical studies actually used for the clinical assessments, so the physicians were tasked with counting the number of malignant lesions of abnormalities that they were able to pinpoint actually in the full dose images, and they compared this with the predictions using the two neural networks. And as you can see here, so we missed so pretty large number of lesions on low dose images, but the cyclid GAN achieved a very good performance where only 4 malignant lesions were missed. So this is one of the typical example where you see the full dose scan, where basically can easily so depict those 2 lesions here, depicted by the rows. These are missed on the low dose scan on the predictions using the residual network, but the lesions can be easily seen actually when the predictions was performed by the cyclid GAN. And the same conclusions, so from the Blount-Hartmann plots can be also said so for similar to the brain PET study. So we also used the convolution neural networks actually to enable implementation of half-time acquisition time for myocardial perfusion studies, so SPECT studies, and then we implemented the deep neural networks in 2 different ways. So in the first approach, we decided actually to decrease the acquisition time by 50%. So we used half of the acquisition time as we did for the PET studies. And then in the second approach, so we reduced the number of angular projections, keeping the same acquisition time. And this is basically the results for one of the clinical studies to compare the full time versus the full projection images. And as I expected, so the full projections and half-time images so significantly improved the image quality, achieving very good performance, so comparable actually to what was achieved by the full-time full projection imaging for myocardial perfusion imaging. And I think these are very promising techniques that can be used to reduce the acquisition time or the activity administered to patients. So motivated by the outcome of comparative assessments of different techniques that enable the conversion from pseudo-CT images from MRI, I'm sorry, MR intensities to pseudo-CT images. So we basically concluded that the deep neural network achieved excellent performance, and then we implemented one such technique for basically generating attenuation maps that can be used with confidence for the attenuation correction of PET data. So basically the convolutional neural network contains two cores, so one for CT synthesis called SYNGAN and semantic structure extraction or SEGGAN. So we used actually the L2 normal and cross untravelous functions. And then the SYNGAN contains 22 layers and the SEGGAN 16 layers. So without going through the details again, so what's important is that this is the MRI and the aligned X-ray CT scan of the patients. This is the segmentation of the MRI. So basically the technique implemented in clinical setting by one of the scanner manufacturers versus what was achieved by the deep learning network. So you obviously see much improved accuracy in depicting the bony structures and the nasal cavities here, so compared to the commercial technique. And obviously you see the bias maps here, so reflecting through the poor performance of the commercial MRI segmentation techniques implemented on the PET MRI scanner that we use in our facility. So this is another clinical study again. So the MRI, the reference X-ray CT, and we compare the deep learning approach actually to the atlas-based segmentation previously developed by our group versus the segmentation technique actually used on the PET MRI scanner. And we look at two different metrics. So without going through the details, if you look to the wise maps here, so the segmentation technique fails completely, whereas the deep learning algorithm so achieves a similar performance to the atlas-based technique, as you can see from the bias maps here. And obviously, so we've got a number of outliers as can be depicted in this case here. So this is an MRI, the X-ray CT image, and obviously an overestimation of the attenuation coefficient in the soft tissue parts of the brain regions here. So we've got a small number of outliers. So let me just skip some of those slides here just for the sake of time. And let me talk about quantification here. And this is one of the techniques that we implemented for neuroimaging studies using different tracers. So one of the physical degrading factors actually when we use positron emission tomography is called photon attenuation and chemtone sketching that degrades substantially the image quality that we can achieve in the quantitative accuracy. And to correct so the PET images for this attenuation effect, so we use concurrent X-ray CT images, and these are the uncorrected versus the corrected PET images. So attenuation correction is a very important part of the chain of the image acquisition protocols, and that this is also very important, especially on dedicated hybrid PET MRI units. So we use also a neural network that enables actually to predict the incorrected images directly from the incorrected data. And we implemented this for different tracers used in neuroimaging, so going from FDG, which is used actually for neurodegenerative disease, characterization, fluoroscopy, for timetamol, and also for DOPA, which is used actually for the assessment of the dopaminergic system for Parkinson's disease, for instance. And I think the performance was very good. So the comparison of the images corrected with the gold standard X-ray CT images are quite comparable to those reconstructed using the deep neural network, as you can see from the images shown here. And we've got some outliers. So as usual, I think this is very common now. And then again, so happy and proud about the achievements of the technique for brain imaging. So we implemented the same technique actually for whole body imaging, and we did the implementation actually in 2D fashion or slice by slice way versus implementation using 3D stacks consisting of 32 slices, and versus a patchy implementation where we've got a patch of 64 by 64 by 64. And this is basically the achievement of the technique comparing the X-ray CT images versus patch images corrected with these CT images, which is using clinical routine, the incorrected images. And these are the images corrected using the deep learning network, which were in very good agreement actually with the images used in clinical routine where PET images are corrected with CT. And again, so we've got also a number of outliers, but what is more important actually is that the deep learning network enabled to compensate for the mismatch between X-ray CT images and PET images in the diaphragm here. This is a very important problem that we face in 20%, 25% of the cases in clinical settings. So we look into the bias maps here. So very good performance was achieved by the deep learning network. And more importantly, so it enabled actually to compensate for this mismatch between the X-ray CT images and the PET images, because we don't have the same breathing patterns between the two sets images. X-ray CT is acquired in a very short time compared to PET images. All right, so I think I've got a large last example here with metal artifact correction. But obviously, I think I don't have the time to go through it. Another application is radiation dosimetry calculations. So let's get actually to the conclusion here. So I think I'm going to just mention very quickly a reproducibility crisis in this that was actually discussed in this science paper it was reported that only 30% of the articles included test data, or 54% included pseudocode. So we're really facing a reproducibility crisis, because most of the technique actually reported in literature cannot be reproduced. Another issue, so with respect to radiology, is there is a large discrepancy between the way the methodology is presented and the results also presented in the research articles. And I think the editors of radiology did a very good job actually in recommending actually, or putting together a set of guidelines how those research manuscripts should be prepared and the methodology described. All right. So I'm going to again to skip the conclusion and just thank my colleagues here who performed most of the work that have been presenting today, and also the funding bodies supporting our research, from the Swiss National Foundation, so the European Commission, and the Fondation Privée des HUG. And I thank you very much for your attention, and then I'll be happy to answer any questions. Thank you very much for your attention, and see you. Bye.